Hello and welcome to Impact Quantum, the podcast where we peek behind the curtain of quantum computing, only to find it's made of lasers, satellites, and the occasional existential crisis. In today's episode, Frank Lavine and Candace Gilhulie sit down with Katana Counz, an experimental quantum physicist who's quite literally helping connect the dots between Earth and space through her work with the quantum encryption and science satellite, or KeySat. For those in the know, she's building the foundations of a quantum internet. Yes, you heard me correctly, an internet powered by the delicate dance of photons. They'll explore how secure communication might soon depend on orbiting lasers, why your body might already be doing quantum things without asking permission, and how this so-called spooky action at a distance could one day reshape everything from cybersecurity to consciousness. So, settle in, dear listener. Collapse your wave function, put your cat in a box if necessary, and prepare to get entangled with Impact Quantum.
Hello and welcome back to Impact Quantum, the podcast where we explore the emerging industry of quantum computing. And you don't really need to be a PhD, although it probably helps, but you just need to be curious. And with me is the most quantum curious person I know, Candace Gilhulie. How's it going, Candace?
It's great. Thank you so much. I'm very excited about today.
Me too. I saw the LinkedIn profile of our guest and I was like, whoa, cool. So many cool logos and stuff on her profile. But
I know. I was geeking out. Don't worry about it. Like quantum physicist. She's on science team. She's founder and CEO of Cubo Consulting Corp, where she's trying to make quantum accessible to businesses. And I'm so excited to talk to her today.
There's also some kind of space thing on there too. We'll talk about that. That sounds really cool.
That's right. That's excellent. Hi, Katana. How are you today?
I'm great. How are you doing, Candace?
I'm wonderful. Thank you so much. I'm really, really excited about today. You have really such a fantastic background.
Thank you. And I did try to fit in all the logos onto my LinkedIn banner of the various projects I'm involved in.
Yeah, that's cool. That's there's a lot in there, and I see a satellite, what looks to be a satellite, and I see hyperspace. Kubo,
Yeah.
I'm not even going to try to pronounce it, but it's Q-E-Y-S sat.
KeySat.
KeySat. So what is you might be the first person we talk to, like what is the connection between satellites and quantum and orbital stuff? I've seen chatter about it, but I've not really heard a lot about it.
That's a great question. Have you heard about the quantum internet or anything like that?
Yes, I have.
Yeah.
I wouldn't say I understand it, but I thought that was mostly like land-based fiber stuff, but apparently there's an orbital component.
Exactly. So with the quantum internet, it's like I said, the quantum version of our classical internet. And so when you start sending information in quantum bits, qubits, now this light, usually we send information using light because light travels very easily, like through our fiber optic cables and through free space, just like straight up to a satellite. But when you start sending quantum information, it's actually very fragile. And if you lose too much of the quantum information, then the quantumness is kind of lost, and you have to start over. And so there's a loss that happens in fiber. Every time we send light, our classical internet through fiber optic cable, it has to go through these boosters called amplifiers, which is basically like little cloners. You're taking a state and you're making it bigger. You're making more copies of it. Well, in quantum, there's something called the no cloning theorem. That means you cannot take copies. So that whole infrastructure doesn't work for our quantum signals. There's quantum repeaters, and we can talk about that later if you want. And so there are the quantum versions of those. But usually that's a more complicated technology, and it's still very in the R&D. And so if you do want to link two users, for example, say one's in America and another could be all the way in Europe. So there's a fiber that links the continents, but this is now tens of thousands of kilometers of optical fiber. And quantum information can only be sent through fiber without having too much loss, up to about 500 kilometers. And so this is good for metropolitan users, intercity networks, things like this. But if we want to link continents, we have to go to space.
Oh, okay. So there's a lot to unpack there. So what's interesting was I hadn't thought about the repeater being an issue because in olden times when things were done over copper, right, there would have to be like a signal booster every X number of feet, meters, whatever you want to do. And that, to my knowledge, it didn't really impact anything unless something weird was going on, right? But yeah, I guess fundamentally you can't do that with fiber and preserve quantum states. Wow, I hadn't thought about that. And two, are this is going to be a stupid question, right? But like, if you have cable going under the Atlantic Ocean to Europe, right? Say, are there every so many hundreds of kilometers like a repeater under the sea, or is it just magically work?
No, I believe there are repeaters on the ocean floor. Yeah, because there's actually a map that because of my role as both a researcher and the CEO of Cubo Consulting, right? I have training that I do on this, and so I have a map that I show that is the fiber optic cables and how far the distances are, and the furthest length is about 40,000 kilometers.
40,000.
40,000 kilometers. Sorry?
It's got to be across the Pacific or...
Yeah. So these are cables that are going from like the Americas all the way to Asia, Eurasia, New Zealand, like that coastline.
Wow.
Wow. So it is across the Pacific. Yeah.
Wow. Yeah. 40,000 miles, like...
kilometers.
Kilometers, sorry.
Well, there's a difference.
Yeah, I'm the only not Canadian on the call.
My apologies.
That's interesting.
Yeah,
no worries.
Scientific units too.
That's true.
Are you trying to sell quantum tech to people who still think AI is cutting edge? Then you need the Quantum Sales Playbook, Selling Outcomes. Not Qubits by Frank Lavine and Candace Gilhulie. It's the first real-world guide to turning deep tech into actual deals with proven strategies for breaking through buyer confusion and closing revenue in pharma, finance, aerospace, and more. Get your copy now for just $7.99 on Amazon. And if you run a quantum accelerator, Frank and Candace will give your startups free copies, no qubits required.
Yeah.
So they have to go to space.
Yeah.
That's interesting. So obviously radio waves or whatever you want to call them, right? Those are also electromagnetic. Those are also light.
Those are light. Yes.
And don't the quantum states are preserved? So if it goes up to the satellite, it sounds like it's more likely to be preserved, right?
Yeah. So with these ground to satellite or satellite to ground links, we're using usually optical wavelengths. So like 1550 nanometers, so telecom wavelengths, or like 850 nanometers, so red, just too far outside of what our eye can see, but it'd be a very, very dark red if you could see it.
Okay.
Because if we were to use radio waves, it's very difficult to detect. So individual particles of light, photons, you have to be able to detect those photons against the background, swamp of radiation that we live in, right? And it's not bad radiation. Like, we want the sun. The sun is good for lots of reasons.
Right.
But it also gives off black body radiation. It gives off solar radiation. It gives off other colors, right? And so when we're picking what color to work on, we have to pick a photon color that we can both receive and send. So create the photons that are single photons, which are quantum. So that means special devices that are driven by lasers. Lasers are actually quantum too. And so this is part of the quantum 1.0 revolution, right? So back in the 50s and 60s, when this technology was developed and engineered, that was quantum physics in action, right? And so what we're experiencing now is doing quantum computers, doing quantum communication with space and things like this. That's the quantum 2.0 revolution.
That's interesting because that tracks kind of how electricity worked, right? Like, first Edison had the light bulbs and all that. There was the research in the 1700s, and then in the 1800s there was light bulbs and stuff like that. And then in the 1900s, which was last century, and that hurts to say. Yeah,
I was
then we
born in
use it as
it.
a, yeah, me too. Gen X pride, right here, Candace. Anyway,
Absolutely.
so,
We're all there. We're there with you.
um, but then it was used for computational ways. So it's interesting how history repeats itself in this regard.
Exactly, exactly. And it makes sense because, for example, with the classical computers, right, we started out manufacturing chips, and we got better and better at making smaller and smaller chips so that we could fit more and more tiny little transistors, little switches that do our ones and zeros. And then we could make them smaller and smaller, and then you have Moore's law showing you how computational power is increasing as we can decrease the size of a chip. But all of a sudden now the chip manufacturers are having to do lithography on the atomic scale. And all of a sudden your wires are now just a few atoms. And now the classical physics that used to make that transistor make sense doesn't work anymore, because suddenly particles can just tunnel through potential barriers, and things that are not possible in the classical world are now possible in the quantum world. But that's now how you create the quantum computer and the qubit.
So it's the quantum computing revolution is coming just in time to rescue us, I
Exactly,
suppose.
exactly. And like you said, it was like a natural progression, right? So we had electricity and so forth, and then the classical communication, quantum communication, and now classical computing to quantum. Yeah.
Interesting.
And that's just one platform. You can do quantum computing with light too. So for example, there's a company in Canada, Xanadu, and they do quantum computers with light. Yeah.
That's amazing. I remember Xanadu came up when Candace did the Canadian country report.
Awesome.
So the frequencies that you communicate with the satellite, I don't want to hog the whole mic there on you, Candace, because I see you're
No,
chomping.
it's okay. Please continue, because my mind is kind of exploding right now. There's so much I'm taking in. Go ahead.
Is that what people call near infrared light? Or is near infrared still kind of
Yes.
visible? Okay.
Yes. Yes. Exactly. Yes.
Gotcha.
Yeah. So infrared is fully like telecom, and then near infrared would be in that like 900 range, 800 range, nanometer range. Yeah. 1,000. Yeah.
So I know this doesn't sound stupid, but like I know biohackers like recommend a certain not radio frequency, the frequency of like red light, and it's still visible.
Yes.
But like it's interesting how that works. And I guess at that point, infrared is heat. I mean, is that a fair way to say it? So I guess the satellite can tell real heat from this particular frequency of heat.
Yeah, so if we were to try to send photons at the microwave range or radio wave range, we wouldn't have a single photon detector that would be able to distinguish between the thermal background noise radiation and our actual photon, which is why we go a little bit higher in optical frequency. And so at the telecom range at 1550, you can distinguish now, like what is a photon and what is noise. And so you can think of it as heat, yes, because as you think of when you're warming up a coil on like one of those old stoves, right? Like the burner. As it gets warmer, it goes from a black metal to a red metal, and then eventually a white hot metal, maybe, right? And so what you're seeing is the optical wavelengths being emitted from an object being heated. Right. And so you can see the colors as it gets hotter, but that's not quantum. That's just a classical thing. That's just black body radiation. So with quantum, if you were to send a 1550 photon to your skin, yeah, you would burn yourself. That was one of the first things I learned. You won't see it, but your eye will explode. So you don't have a blink reflex.
Okay.
So don't get the laser in your eye.
Gotcha.
Yeah.
How do you explain what you do to, the layman, like, the 15-year-old cousin, like,
Yes.
how do you explain what it is that you do?
So I get that question a lot, because if you just say, I'm an experimental quantum physicist, they're like, what does all of that mean? So usually I start out small and I say, well, I'm a scientist, and see how they gauge, right? And if they want more, then I say, okay, have you ever seen the show The Big Bang Theory? It's on TV. I'm like the combination of Leonard and Penny. So Leonard's the experimental physicist, right? If they haven't seen the show, then I say, well, one of the projects I work on is with the Canadian Space Agency, where I usually, usually telescopes, you think of telescopes looking up at the stars and collecting the light from the stars. But telescopes can also be used to send the light up to space. And so with the KeySat mission, the quantum encryption and science satellite, we're using a telescope and a special quantum source, a laser, that's a special quantum laser, and it will send light through the telescope up to the satellite. And so why do you want to do that? Because if you want to have secure communication from, say, Vancouver to Toronto, again, you can't go across the entire country in just fiber because the quantum information will get destroyed. And so the best way to do it is to have a ground station, one of these telescopes at, Vancouver, another one in Toronto, for example, right? And then link it that way. So in this mission, our ground stations are at the CSA headquarters in Saint-Hubert in Quebec. And then the university I work with, the University of Waterloo at the Institute for Quantum Computing. So Waterloo, Ontario, there's a ground station there. And then also in Calgary. So Calgary has a quantum ground station that's currently active, linking with other missions. And so they're part of the science team. And so that's also a ground station in Canada.
That's very cool.
That's fascinating. And I'm going to ask a silly question. But is it, when you're saying that you have these different telescopes and they're sending, lasers up, so are they all connecting up in space so that they can communicate with each other and send information back and forth that way? Or is it like
sort of via the satellite. So one ground station will connect with the satellite, and then the satellite will continue on its low Earth orbit to another ground station, and then there'll be another link.
Okay, so it would go up from Alberta to say Saint Hubert, and then
so it would be a single pass because the satellite only has one telescope, only one receiver transmitter, and so it can't see two locations simultaneously. But there are other missions that have been demonstrated. For example, the Meteus quantum satellite mission from China from several years ago, they did a secure video call between two locations, one in Europe, one in China. And their satellite was a quantum downlink with two telescopes. And so they could see both locations simultaneously. And then they basically did what we're doing right now, but it was quantum encrypted.
Wow. Yeah. I have a lot of questions. So obviously, if it has to use the satellite, there's going to be a certain amount of latency, right?
Latency? Is that what you're...
So like I grew up in New York City, and since leaving, I want to live in more rural areas, right? And like one of the issues with satellite internet has been the latency, right? So because it has to go up and then back down. Is that an issue? And I never use satellite internet so that I'm aware of, so I wouldn't know what the actual experience is. But somebody said like you don't want to do it for anything kind of real time, like either gaming or calls. Is that a barrier for you all?
I see what you're saying. So right now, because like, for example, the KeySat mission is a tech demo. And so having real-time user access to the quantum encryption is just not feasible right now with the technology. So there is sort of a latency. Like, for example, the sun is really bright. And so it's really difficult to do quantum links during the day. It has been demonstrated, but it's just difficult. And so usually these quantum experiments are done at night. And so that already, you're going to have to do a secure key storage, for example, on site. And every time there is a viable pass that you start storing those keys, and then that's how you would be able to give them to your customers or your embassies, for example. But having a real-time quantum internet, quantum connection, that's still in the future.
Right.
Plus, we need that repeater thing.
I was going to say, like, doesn't the satellite then, isn't the satellite function kind of like a repeater? And how do you get
now, it's only going to be storing classical information, but yes, we would want quantum memories. On satellite. And so, like I said, there's several universities, like for example, the University of Alberta, they have Lindsay LeBlanc is working on research with quantum memories, quantum repeaters. So using atoms to actually take the information that's in the light, and then the light interacts with the atoms, stores the information in the atoms, and then you can tell the atoms when to let it out again. So it's like a quantum hard drive.
Wow.
Yeah.
So that's what you meant by quantum memory.
100%. Yes. It has to be a medium that will preserve the quantum information. And so because classical devices, it's like analog versus digital. This is a metaphor, not an actual. Lots of people get mad when, you claim this is not metaphor here. So in the quantum world, right? Just like what you were talking about, the red light sensors, right? Our bodies are quantum sensors, basically, right? We're biologically quantum. So when we try to model like a molecule or medicine using a classical system, a classical computer, we have to make all of these shortcuts, assumptions. We're not doing the whole model. So when you're storing quantum information, we have to store it into a quantum system. You can't store it into a classical system because then again, you're truncating, you're simplifying, you're removing information. There's just stuff that you can't store.
Right. Yeah. There used to be a term. This is another type of nerd term, but I think it was called flunking in Windows. In Windows, like if you were taking something in a 32-bit memory space, you were cracking it down, not crapping it, but like trying to stuff it into a 16-bit memory space. I think it was called flunking.
Okay.
Yeah. But yeah. So, but you lose a lot, like, and you would want to avoid that if you could, but if you had to do it, you could. But that's interesting.
But in the quantum case, it doesn't even work.
It doesn't even work. Okay. So you couldn't even do it. It wasn't even an option.
Yeah, but then analog versus digital, that's why I wanted to bring that up, because it's like with the analog, like a record, right? When you listen to music on a record, you have all the vocals, you have all the instrumentation. It's not been truncated. It hasn't been chopped up into little bits and digitized, right? And you can hear the difference. That's why records are coming back.
Right.
Yeah.
No, that's true, because what you're getting with digital audio is getting a sampled version of that, and there's only so many samples per second.
Yeah.
This is why, Candace, when I export it, I pick 96 kilohertz, because it's like those are 96. She can keep me honest on the math here. It's 96 samples per second that it tells you, right? So if it were a musical recording, it would sound really terrible, right? But for voice, you can get away with a lot more because the human ear is tuned to the voice frequencies and all that. But
we fill it in with our subconscious.
Yeah. Well, apparently your vision, the raw signal that comes out of the retina is really, really lousy too. And the brain kind of like fixes it.
Our brains are very potentially quantum devices themselves, right? Like there's all these arguments about quantum consciousness. Is there quantum processes that are undergoing with our neurons? Some of it gets into metaphysics. And so you can't, but there are professors like at the University of Calgary that look into consciousness and quantum consciousness and do experiments with actual neurons.
That's cool. I wonder, like, because like the thing with metaphysics and stuff like that is like, when you get to philosophy, it's, kind of borders that philosophy/theology. And it's like, well, how do you really experiment with that, right? The typical scientific method can work, doesn't always work. I don't know. Like that's, I always love it when one discipline kind of bleeds into another, right? That's where it gets real interesting. And I can totally see that. That's why one of the reasons I love this, right? Because it's like, well, it's not your usual like computer science type stuff. Like it really blurs the line. Wow, that's interesting. Well, I also heard, again, sorry, Candace, this is a bit of a tangent. One of the things that people are saying that some of our senses are also quantum driven, right? Apparently, there's a poison, I think it's cyanide or something like that smells like almonds. Smells like something else. And then like people are like, well, that's kind of weird. And then somebody posited the idea, well, maybe the outer electron shell of both of them are the same. And it turns out that does kind of track. I don't know if they've proven it, but it's kind of like, well, that means that your sense of smell is driven by some kind of quantum effect of that electron. I don't know. I'm not a physicist, and I didn't stay in a Holiday Inn last night, so But I thought that was interesting. Like, it's not necessarily this weird exotic thing we don't experience, right?
Correct.
It may show up around us, right? Like in very subtle ways.
Yeah. Birds have magnetic sensors to navigate using the magnetic field of the Earth.
Mhm.
Other animals too. And we can use quantum devices, quantum sensors to all do the same thing and have a portable GPS unit. So if you lose sight of your satellite, if you lose connection with your satellite, usually you have no idea where you are in the world. But yeah, there's quantum sensors that have been developed already and have been field tested and are being deployed right now. They can give your location based on the magnetic field. So if anything,
Wow.
it's almost like we're starting to create technologies that model what nature already does.
Well,
That's
right, like,
cool.
because like photosynthesis, essentially,
Mm.
if you think about that, that has to
Mm-hmm.
do, there's got to be quantum going on there,
Mm-hmm. Yeah.
right?
Yeah.
And so if
They've
that's
been
already
looking at,
happening, I'm sorry, go ahead.
sorry, I think there are some studies about quantum tunneling possibly. I have to check that, but I remember that there was some people were looking into the transport of certain nutrients, I think, through the plant and whether that was a quantum process.
See, and that could
Interesting.
also be related to how your body deals with different types of enzymes
Hmm.
and how they react in your body. That could be completely, a biochemical, like quantum chemistry type of thing. And,
Yes.
that's just we don't know about it because we haven't, I don't think, well, I'm not saying, I'm sure someone has turned it inside to figure it out, but um yeah, it's fantastic. Also the way you smell, that there's
Hmm.
apparently,
Hmm.
quantum involving how you take in different types of odors and those
Hmm.
molecules. So that's
You're totally right.
fascinating stuff, right?
Hmm. Hmm.
I love
I-
it.
Well,
it-
we
it-
are made of atoms, right?
Mhm.
So at our core, we are quantum.
right, that's true. Like everything around us is, the old
Yep.
joke, like don't trust atoms, they make up everything, right? So, um, but no,
I've
I
heard that
mean,
one.
oh, you ever heard that one? Oh, okay, that's funny. So you feel free to reuse it. I didn't invent it. But which always gets to an interesting point because you mentioned this when the chip designers, as we get smaller and smaller and smaller, quantum normal, I'll call it normal, right? Like
Hmm.
what we expect to happen with electrons and whatnot, they start acting differently. Is
Exactly.
there is there a term for that? Like, kind of when quantum stuff tends to happen more. Is it like a border? Like, like I'm crossing from Virginia into Maryland. Is it like a strict line, or is it kind of like a gradual thing where, well, it starts coming up and then it starts coming up a little bit, and then kind of like when you're driving from the city into the country, right? It's not
Yep.
like this neat line. It kind of like, first the sidewalks go away, the lawns get
Yeah.
bigger, right? And then you have
Yeah.
farms. Is it gradual? Is it subtle? And is there a known um, scale where that happens?
This is a fantastic question. This is an active research question in my field right
Oh,
now.
okay.
There are experiments that have been done recently, and I can find the publications if you're interested,
Yeah, we'll put them in the show notes.
where they literally are trying to determine where is this boundary between the classical world and the quantum world. And so one way with light that you can do that, like I'm an experimental quantum physicist, like I said at the start, right? And what does that really mean? I play with light. I do experiments with light. And when you have a quantum state of light, it means that you have like a very small amount of photons, say 5 or 1 or something like this, right? It's a very, very small amount. To give you an example, a light bulb gives off like a standard, 60-watt light bulb gives off like trillions of photons a second. Trillions a second, right? So it's a classical thing. And so, well, what if I was to take my quantum, system and I start adding photons and I make it bigger? Or I take a big quantum system and I start removing photons and make it smaller, right? And so where is that boundary? And they've even tried to measure the collapse of the wave function. So in the quantum world, you have this like probability, right? It's like I don't know what it is, but I can give you a probability or a wave function that describes what it could be, right? It has all these parameters that say, okay, the weightings, right? So it could be this state. It's most likely a single photon state, but it could have like 10% of a 2-photon state. It could have 1% of a 3-photon state, like that, right? So that's a probability distribution, right? And so they tried to measure when it will actually collapse. When will this, in something that's in a superposition state, like Schrodinger's cat, right? Is it dead? Is it alive? I don't know until you open it. So they tried to actually measure the moment of that hypothetical cat collapsing.
Right.
Yeah.
Okay.
And the answer is you can kind of measure it, but every time you try to get a clear picture, it does something funny. Right? Like with the uncertainty principle, you try to know where something is very, very precisely, and suddenly you have no idea how fast it's going. And so you knew where it was really, really precisely, but now it's flown away.
Yeah, it's almost like the universe is like playing hide and seek with us, isn't it?
Yes. Yes.
Interesting.
And with the uncertainty principle, it makes total sense though, right? Because the way you see stuff is light is bouncing off those objects and reflecting and coming back to your eye. And so light actually does impact a force. So like, for example, with satellites, you can deploy a solar sail and you can use the solar wind, right, to direct and help push your satellite. So you can do the same thing with thinking about it with the object. So when you have a microscope, you send photons, you send particles of light that are very bright to get a nice bright picture back. And then we're like, okay, now the photons are putting too much momentum onto our tiny little microscopic objects and they're moving. And so, okay, now we'll use an electron microscope. So instead of sending light, we're going to use electrons, which have like a different property. They don't diffract, they don't spread as much. And so you can get a cleaner picture. But still, when they hit the object, they will move the object a little bit because they're imparting like a force, right? And that's what the uncertainty principle is saying. It's like, if you're trying to figure out exactly where something is, you have to like really hit it with something that bounces right back to you to get a really precise answer, which means you had to send in something with lots of energy, lots of momentum. Now the thing that you just tried to measure, it's taken all that momentum and it's shot away in some random direction. So you have no idea where it went.
The act of measuring a system messes with the system. It's kind of like when you were a kid and like they had the principal would step into the room.
Yes.
Like to observe the class. I was like, this is not the act. Like it would totally change. Yeah, it would totally, like change, right?
Yeah.
You said something about solar sails. I didn't think that was photons. I thought that was like maybe they're the same thing. Charged particles coming from the sun that actually did have mass.
Yes, they do. But you can also get what's called radiation pressure. And so you can also do it with light. They've done it in the lab too. Just photons. Yeah.
That's wild.
Yeah, but you're right. There's also a solar wind, and so there are particles too.
So what are those? Those are charged particles. What does that mean?
Those ones are electrons and protons and
so actual legitimate, like normal, not normal, but atoms with like some energy behind them. Obviously, there's physical kinetic energy, but there's probably some kind of other voodoo in there too.
Yeah, so in this case, it would be the kinetic energy, I believe, that would be imprinted onto the solar sail, and
okay.
But the photons will also imprint, because they have momentum. They have energy. They're moving at the speed of light, so they have momentum.
Interesting, but so little mass, but they're going so fast that kind of cancels it out, right?
Exactly, and if you have a big solar flare, that's a big, burp from the sun.
Right.
You'll definitely feel that. It knocks out satellites also. Like that's the other problem, right? With the that's a whole other issue with the radiation and damaging to our electronics.
Right, and you're both far north enough. You probably see the northern lights quite a bit.
Yes.
So.
So, I mean, I completely understand why you're in education. I mean, you really have a beautiful way of breaking things down and then explaining it in a way that makes it really exciting. So so you really can demystify quantum technology. So when did you make the shift to your consultancy?
About 2 years ago. I'm doing the jobs in parallel because I still want to be a part of the KeySat mission. And I find it's really helpful having my foot still in the research side. So I'm keeping my pulse on what's going on, and then in the industry side, and then trying to act basically as a quantum translator.
That's a good point, because I think that's totally needed. And I think you would be one of the few people in the world that can answer this, like as someone who did come from academia.
Yeah.
Like what's the industry feel like now? Because when I went to my first quantum only conference, right? All of these are lanyards from like tech conferences, right? So I've been to a lot of tech conferences with all the good stuff, the bad stuff that go with it, right? Like, but I noticed that and I've been to a couple of academic conferences. They definitely have a different feel to them. What was interesting is that the quantum one I went to in DC kind of had a little bit of both. It was kind of like, they put a little bit of milk in the coffee, or, you know what I mean? It was kind of like, wasn't really, it was an interesting experience because it had a lot of the trappings of a typical kind of tech conference, but really like dialed, kind of like to a lower level to, I think, appeal to maybe the more academic setting that it was in. And it definitely had more of an academic taste to it than your average, tech conference. What's your opinion on like where the industry is now? Do what's your take on that?
Yeah. So do you find at the tech conferences that the quantum is more like hyped up?
Everything at a tech conference is hyped up, right?
Okay.
So it's not so much quantum. Quantum barely comes up. I think I was at a
More AI, right?
It's more AI right now, right? And quantum doesn't really come up. I was at a defense industry conference a few years back, 2021, where IBM had a booth, and a big part of the booth was their quantum stuff. But other than that, it didn't come up. I would imagine now it's probably a little different, given the encryption type stuff. But no, I'm just saying, like, the general feel of a tech conference is kind of showmanship, right? Like kind of like brashness, and you're getting free little like squeeze things, right? Like to varying degrees of crass commercialism, right? It would be a good way to put it. But it was fascinating to see it was way more mellow and tuned down at a quantum business summit, right?
Yes. So I do find that when I'm translating this information, I walk that line between hype and reality. Because some academics will definitely deliver the information in more of an academic way. And so they want to be very technically correct. And the meaning behind it is lost for anyone that doesn't have a PhD in quantum. So the person listening who could have a PhD, but they are a mechanical engineer, right? And they're listening to this person, and they're just like, you lost me in the first 3 minutes. Like, I don't even know what you said. Like, you used 4 acronyms, and I don't know any of them. Like,
or God forbid, it's somebody in the C-suite, right?
Exactly. Which is why I specifically created online training courses for executives, because I want them to be able to engage in this industry without being scared of all of the technical jargon that drives even myself. Like, I can get lost listening to some of these talks, and it's like, if I don't even know what you're talking about, and I have 15 plus years experience in the field, like, how is anyone else going to have a chance, right? And so to answer your question, we will never need to have, I'll never say never. It makes very little sense that you would need your own personal quantum computer. I'll say that right off the bat. So in the future, I don't think you're going to need a quantum Mac or a quantum PC, right?
No Q phone on the horizon.
Yeah, a Q phone, right? Now, the quantum encryption part, maybe your phone will have, hopefully will have algorithms that will keep your devices secure from quantum hacks, right? So that's a very important thing to talk about. Because a quantum computer, while it has all of these advantages, it also could potentially hack a lot of our public key encryption that's currently used for online banking, for shopping, all these things, right? And so that's why there's also, post-quantum cryptography and things like that. And so the projection from the industry is in the next 5 to 15 years, we will have a quantum computer capable of hacking RSA encryption. Currently, right now, there are quantum computing devices, the cloud systems that you can access. You can learn how to program on a quantum computer using like 10 bits, 10 qubits that you get access to for free. Lots of these companies have tutorials that are free or very, very low cost to access. But you probably won't need a quantum computer for every day, right? Like this is like most of our classical computers handle what we do. It's just these really, really complicated, difficult problems, like the traveling salesman problem, right? There's so many applications of that in so many different industries. Anytime that you have to move something, goods, whatever, from one location to another or to multiple places in a city, Uber Eats, things like this, right? These are very complicated optimization problems. And so anything that's currently being done with AI optimization, you could try potentially doing that with a quantum computer. And the advantage is it can give you solutions that AI systems may not ever find. Because an AI system, a classical system, you're going to try a certain number of combinations. It's going to do its search, but it's going to do its search based on the algorithm you tell it, the parameters you tell it. Whereas a quantum computer, a quantum device, like for example, the D-Wave system, a quantum annealer. So with this superconducting circuit, it's actually going to do the calculation by quantum. Like it goes into its lowest energy state, the quantum circuit, and that's the answer to your question, to your problem, to the optimization problem.
So for all my AI people out there, and she can correct me if I'm wrong, traditional conventional algorithms in AI can only find the local minimum, but you're not guaranteed that that local minimum is the minimum. Whereas a quantum system would find the minimum full stop, right? Is that
the global? Yeah.
Yeah, the global minimum. So which is
100%.
a fancy way of saying that you get to your answer. You get not only to an answer, but you get to the ultimate answer. So
that's exactly right. Yeah. That's right. And there's big corporations that are using these devices now to optimize things like that, like Save On Foods.
Really?
Yeah.
That's the supermarket chain, right?
Yeah.
That would make, at first I was like, oh, that sounds silly. I was like, no, logistics.
Yeah, exactly.
Yeah.
And the transportation industry and airplanes, like optimizing turbines, the balancing of turbines is actually very, very difficult. There's just those big propeller things.
Right.
Yeah.
Interesting.
Yeah. Any optimization problem, it's possible that it could have a quantum solution, and if not, you don't know, right? We're just making this. It's like
you won't know until you try.
Exactly. It's like you have a tricycle and you're trying to imagine what the 4x4, version of that is going to be. And it's like, we're still at the tricycle stage, guys. Like, we're happy that we can go straight and we can turn when we want. Yeah.
No, that's a good way to put it.
But it's very powerful. Even though it's only, in this metaphor, a tricycle, it's a powerful tricycle. It's already beating some classical computers, but it doesn't have. So this is where the academic will step in and say there hasn't been the ultimate proven quantum supremacy or whatever you want to.
I'm glad you brought that up, because one of the things that Candace and I have noticed is that there's a lot of, for lack of a better term, Debbie Downers, right? So like someone will come out with a startup, right? Now, obviously, and I don't think these are hype. These are not hype people that are doing this, but they'll say, we announced something, right? And then they'll say, but then suddenly there'll be like a bunch of PhD types, no offense, not present company excluded.
I got friends that you're talking about. I know exactly what you're talking about.
Well, actually, and basically parrot something almost exactly word for what you just said. Yeah. Now, I seem to remember a little bit of this in the early AI days. Is this just a growing pain or is this just a part of the process of going from an academic-based discipline to a commercial discipline? Is there some other dynamic I'm not thinking of at play?
You definitely have the fact that the industry and the people that make the money, right? They want to be able to make flashy claims in the news because that helps with stock prices. Like that's just part of the
funding.
And hedge funding and things like this, right?
Yeah.
But in the academic world, you then have the the very, very hard mathematical definitions of what is a quantum state and what would be a problem that a classical computer cannot solve, but a quantum computer can. And so there's very, very academic, rigid descriptions of this, right? And so that's where the clash is, because it's like a system could be demonstrated to be quantum, to be a quantum system, to be doing quantum computing, but it's not a quantum computer. And so the company still wants to say, we made a quantum computer. And then all the academics will say, no, you didn't, because you don't have error correction. You don't have this many qubits. You haven't been able to do this algorithm.
It's
have you
not
done Shor's
Turing
algorithm
complete.
yet? It's like, show me your Shor's algorithm.
Right.
Yeah. And so that's where I step in and I try to say, hey, we have these quantum systems. They are doing quantum operations. They can be applied in selected, these problem sets that are still real problems that are helpful to right now, like the industry, the energy industry, right? Trying to manage all of these distribution centers. Now with AI, you have so many new power plants being created. You can actually use quantum sensors to help improve the syncing of the electrical signals from those distribution grids. You can use, this is huge. There's quantum optimization also to help with the scheduling and things like this.
And whatever logistics it takes to keep the plant up.
Yeah. And so when you have the academic come in and say, oh, but it's not a quantum computer, so then 90% of the people will be like, oh, okay. And then they're not interested anymore because they think that it's not a quantum computer. It's not real.
It wasn't that long ago that they were saying, well, that's not real AI, right?
Exactly.
So that's why I'm like, maybe this is a pattern, right? Because I like to see patterns, right? Sometimes maybe a little too much, but history does, if it doesn't outright repeat, it definitely rhymes, right? And there's certain themes that will kind of like pop up now and then. I have one question though, and so I've always wondered this. Laser is actually an acronym.
Yes.
Isn't it?
Yes.
But I never understood what that meant. I know this is a bit off topic, but you actually are an expert in this field, and they're not like not everybody is an expert like you in this space and can explain it away. So what is the acronym and what does that acronym mean?
Okay, so laser, so light, amplification for stimulated. So because you're stimulating atoms to release light, light, amplified, stimulated emission, radiation, something like
that, emission of radiation, which I remember that doesn't make any sense.
So what happened was, think of synchronized swimmers. Okay, I love metaphors. Think of synchronized swimmers. We figured out back in the 50s and 60s, you could take an atom and then you could bombard it with light, with a different type of light, and it would then cause those atoms to start emitting light that are all in sync with each other. And so it's like synchronized swimmers, and all these little photons, all their little wavelengths, they're all synced up. And so now instead of having randomness, you now have this like choreographed stream of photons coming out of your device.
Oh, so the radiation isn't like plutonium. It's
in phase. So it has yes. Yeah,
but it's
not
so like plutonium.
It's
not going to give you cancer, right?
No. This isn't
not radiation in the common sense of whether it's
no light radiation. Yeah, no, this isn't atomic radiation like beta decay. That's actually electrons.
Oh, but that'll
and
kill
alpha
you
decay
because of the frequency, right?
So then the electrons, they would be carrying energy, and then their interaction with your cells, I think could then. I'm not an expert in this, but break apart
the DNA and cause trouble.
Exactly. Yeah.
Okay.
Whereas gamma radiation, people think gamma rays, right?
Yeah, like Bruce Banner.
That is photons.
Oh, interesting. I didn't know that.
Yeah.
Is that why it can like punch through like more stuff and you need more?
Potentially.
Okay.
Yeah, because higher energy light could maybe get through. Yeah. And then alpha radiation is actually the nucleus of helium atoms. So it's 2 protons, 2 neutrons. It's the nucleus of a helium atom. Yeah.
Interesting. No, I remember seeing a diagram, and it was basically like a piece of paper will stop alpha.
Alpha, yes.
And then you need a little more for beta, but not like a ridiculous amount. But you need like lead and like serious like serious metal to stop gamma. So
Yeah.
that's
And there's gamma
interesting.
rays from the cosmos too that will streak through.
Right.
Sometimes when the early astronomers were exposing those plates to get the starlight, so they would
Yeah.
capture light onto a photonic plate, you would get streaks, and sometimes those streaks were actually cosmic rays or gamma rays.
And is that why astronauts, when they're sleeping in space, even though their
Mm.
eyes are closed, like they see stars or something like that?
I don't know about that.
That's what I heard. Like they close their eyes and then like they'll just see like flashes and
Oh.
supposedly, I don't
Well,
know.
they're
I've never
also
been
in
to
the
space.
well, not in the radiation belt, but they're being exposed to.
Right.
I mean, and they're shielded, but like, who knows what you would be seeing when you're in
Yeah, there's only
space?
but
You're
so
right.
much.
Yeah.
Yeah. Interesting. So many questions, so many rabbit holes to go down, but thank you for explaining the whole laser thing because I was always bothered by that. Like, and it's one of those
Yeah.
problems that you don't really think about, but like you're like in the store at Safeway and you're like, or you drive in and you're stuck in
Yeah.
traffic. You're like, I always wonder, one of these days I'm gonna get in front of someone who's
It,
an
it,
expert
it causes
and
a
I'm gonna ask.
cascade. That's why it's
Right,
called
right, right.
stimulated emission, right? And so you get some atoms
And
excited and it
that's
gets more
so the
atoms excited
coherent
and yeah.
coherent is the type of light it makes, right? Because they're
Yes,
all in
coherent.
sync.
Yes.
So, do you ever see the movie Real Genius? It's funny. There's a funny scene in it.
No,
I
I don't
always
think so.
remember like fragments of movies. It was a Val Kilmer movie in the 80s.
Mm.
And there was it was basically a bunch of kids out at Caltech or something like it was basically what it was about. And this one kid who was like a teenager, super genius, goes to the school at like 15 or something like that. And that was one of the plot points. But he's talking to his dad, who's not a genius. His family's not, so he's totally misunderstood. And he's doing a science project about lasers. And he goes, "No, you see, what makes it different, Dad, is that the laser's coherent. The light here is coherent." And the guy goes, sipping on his beer, goes, "So it can talk." So no, like that joke is kind of stuck in my head. But if you've not seen the
That's
movie,
great.
I recommend it. It's a very classic kind of 80s movie.
Nice. I'll have to look it up.
Yeah.
Yeah. So yeah, a
Sorry.
light bulb is incoherent.
Right.
Light. Yeah.
So it can't talk. No, just kidding.
No, exactly.
Um,
Hey, when the light bulbs start talking to you, maybe you're incoherent.
yeah, it might be time to seek a professional help. I want to be respectful of your time, and I have a hard stop too. Any final questions, Candace? It would be cool to have you back and like maybe like another time where like no stupid questions. Like maybe we'll collect questions from like people and because you're really talented at explaining kind of like.
Oh yeah.
Yeah.
Thank you. Thank
I've
you.
learned
Yeah,
so
I mean, I have
much.
some slides and things, so we can
That'd be
always do
cool.
another episode if you want.
That
Yeah.
would be awesome. I'd really
Yeah.
appreciate that.
I
I'm
wanna
good at
talk more
talking,
about
don't worry.
quantum in the body. I want to talk about quantum in the body.
Yes.
That was
Yeah.
just blew my mind, and I thought, oh my God, all these things that are already happening, they're all around us, and we're being silly to think that it's not happening that way. And
Maybe it's not this weird exotic thing. We're just finally noticing it, right?
Exactly. Thinking of another way to rationalize it maybe too, right? Like think of like Eastern medicine versus Western medicine, right? There's a lot of things in Eastern medicine that Western medicine doesn't acknowledge or understand or be able to measure, right? And so with some of these scientific approaches, it's almost like a Western approach, and then like the quantum consciousness side is more like an Eastern medicine approach, right? And so like it's very possible, like when someone thinks of you, right, and then all of a sudden you think of them, and then all of a sudden there's a phone call, right? Like how many times does that happen?
No,
right?
There's something to that, and you have to. I think we all science in the West is basically the great grandchildren of empiricism, which is summed up. I went to a school known for philosophy, and I have a computer science degree from there, so my mind is really warped because of that. But empiricism is basically a $10 word to explain if I can't see it, touch it, taste it, smell it, or measure it, it doesn't exist, right? That, I mean, it works for a lot of things, right? It did do a lot of, in the West, we rooted out a lot of our superstition, right? But along with that, we threw the baby out with the bathwater, right? Because there was a lot of things in Western esoteric traditions that did kind of, talk about a lot of the same things as Eastern things, right? But we threw the baby with the bathwater out during the Enlightenment, and we're feeling the effects of that to this day.
Yeah, and this could be the correction.
Yeah. Well, now, I
Quantum
mean,
correction.
yeah, quantum correction. I like
Yeah.
that.
There you go.
Awesome.
All right. Well, it's been great talking to you. And where can folks find out more about you and what you're up to?
Well, please look me up on LinkedIn under my name, Katana Counz. My company has a website, cuboquantum.com. And I also have a partnership with NATE, the Northern Alberta Institute of Technology. And so I'm offering online quantum training for both executives and engineers. The next cohort starts in November, and we're going to be running these classes every 3-4 months. Yeah, online. So you don't have to be located in Canada.
Awesome.
And I'm the teacher. So
Awesome.
if you
Well, that's good
liked
to
what
know.
I said, come learn more.
Awesome. Well, that sounds great. And I'll let our AI finish the show.
And that, dear listeners, brings us to the end of another episode of Impact Quantum, where we've learned that in the world of photons and qubits, distance is relative, lasers are friendlier than they sound, and the universe is basically one big cosmic Wi-Fi network, though with slightly better encryption. A huge thank you to Dr. Katana Counz for helping us unravel the mysteries of quantum communication, and for reminding us that what sounds like science fiction is rapidly becoming just science. If you enjoyed today's episode, or if your brain is now vibrating somewhere between enlightenment and confusion, be sure to subscribe, share, and perhaps take a brisk walk to let the superposition settle. You can find more from hosts Frank Lavine and Candace Gilhulie along with past episodes, show notes, and the occasional quantum pun at impactquantum.com. Until next time, I'm Bailey, your resident British AI lady, signing off from the space between bits and atoms. Stay curious, stay entangled, and remember, in quantum and in life, observation changes everything.